My name's Dominic, and I'm into distributed systems. Um, so last summer, this was the Southern Hemisphere summer, so it was only about 6 months ago. I was always a back end guy, so I was like, what is this front end thing? So I started playing around with single page apps, and I think this happens to back end people who come to front end, like MVC. It just doesn't feel right. I looked at, I was like, how do people do this? I looked at Backbone, et cetera, et cetera. And so what my intuition really wanted was something where when you change something in the UI, it sends an event to the model, and then when the model changes, that sends an event to the database, and vice versa, because the database, whatever the database means, could change. Because another user could change the database, and that changes the model, that changes the UI. That seems simple and elegant. That's how I want things to happen. But that works with the UI and the model because they can communicate synchronously, so it's really easy. But unfortunately, a database is kind of a different shape to the rest of your application. Like, you have this one thing off over there, and you have to send it a request, and then it tells you what is true now. And if someone had made a change while you're making the change, then you might get a different answer from what you're expecting. So I had this funny idea that, well, hang on, if I want to send changes, don't I already have a thing that's all about sending changes? Isn't Git just about sending changes to each other? And so Git is a distributed version control system. And I guess if your app runs across multiple computers or phones or whatever, then that's distributed as well. So what if we just made something like Git, but in JavaScript? So I started looking into how Git really works. Oh, who uses Git? Cool. And who has recently merged a different branch, like a pull request or something? Cool. Okay, very good. You'll know what I'm talking about. So Git instead of storing the state of your files, Git stores the history of your files in terms of the changes. Now, this makes a tree because you can have different branches, and each commit points to the previous commit with a hash. And so the hash of a commit is the hash of the commit, the contents, the change, plus the hash of the previous commit. So you can't change old commits without invalidating new commits, and that's really good. It's quite an interesting feature for security. So there are sort of three parts that enable Git. There's diff, which is a program that calculates the difference between two files. Diff3, which does 3 files, and patch, which applies a change set to a file. So a three-way merge, that's what you're doing when you merge two branches. So diff, that was written in 1975 by Doug McElroy, who you might remember if you, he had basically invented streams. So yeah, this is how you use diff. So you just diff like a new file, an old file, and then you can pipe that, and then you can take the output of that and you can use it to patch the old file. Now, diff3 is more interesting. Diff3 wasn't written until 1988. And it computes the difference between 3 files, between, say, my version of the file, your version of the file, and an older file, which both of those files started as, some time ago, like an older version. So Concester, I was working on this in the library once, and this book on biology found me, and Concester is a biological term for the common ancestor. So, the common ancestor of birds and lizards as dinosaurs, or stuff like that. So diff3 was actually invented by Randy Smith, and then it didn't actually enter academia for 19 years, and there's a paper on it now, but that paper was only written quite recently. So it's quite interesting too that this was like the last thing you needed to make Git, but it was also about preceded Git by a long way as well, because Git was written like early. Does anyone know? 2005? Yeah. So Git could have happened a long time ago. If you ever travel back in time and you find yourself in the early 90s, please invent Git. So, so this is, okay, we just revealed you guys already know this. So there's my version, your version, and so C and E and F happened on different computers at different times without communicating. So basically this means that C and E and F could not have caused each other because no messages have been sent. This sort of E means that you know about B, but not about C. So then what we can do is we generate a new commit that merges the differences from E and F and from C and puts them into a new event, a new state called G, which makes sense in the context of both branches. Now, Git lets the human handle the weird cases where there's a collision. But if you had a real-time application that was doing distributed data, you'd probably, in most of the applications I imagine, you'd probably want to do that automatically and just let the humans deal with that afterwards, rather than being like, hey, we've changed this thing, what are we going to do? That makes sense for code, though, because code has to be correct. So, and you've got really smart users. Okay, so I was like, this doesn't look so hard. What if I just re-implemented Git in JavaScript? And so I started working on this, and I've got this module snob. So it has like every node is basically its own database. Well, database is a term I'm abusing to call this thing a database, because now you can have a database that runs in memory in the browser and persists to local storage. But it means you get offline use for free because you've got your own local database. And then when you connect to another database, you can send stuff there, and then it makes sense there, and you just sort of... a use case I really like to imagine for this is imagine robotic explorers. Now, they're off exploring down like canyons on Mars or something like that. And they only see each other occasionally. Sometimes they're completely out of radio contact. But they have like shared information, and then they travel off, and then they find each other again, and they're like, oh, what have you learned since last time I saw you? And they can exchange that information and then add it to their own data banks. So, so you have the snob thing, and this is important. All the modules I'm going to show you work like this. So you have these serialization patterns. Like you just connect them together with a stream. So the repo has a create stream thing, and this is so you've made a connection from a remote stream. You just connect it to your stream that you have, and then they sort it out, and now they know what each other's talking about. You can also just like write the repo to disk, and that will just make an append-only file that has everything about all the changes will end up in there. Even as you make new real-time changes, it will just be appended on the end. And you do the same thing in reverse. Oh, sorry, that's a bug. That should say create read stream, and that should say, sorry. Just reverse those two things. I was finishing off this morning. Missed that one. Yeah, but it's just append-only files and reading append-only files and communicating with line delimited JSON. It's really simple. So, but then I've had a few problems. Git is actually kind of complex. It took me 6 weeks to get this to a point where I could replicate data in a browser. I thought that was pretty good at the time, but then I was like, it's kind of cumbersome to attach this to Backbone or something like that. And most apps don't need to know everything that's ever happened. Like if you are, working on a to-do list or something and moving things about, or you're making a game, it doesn't matter. You don't need to know everything that ever happened in that level to know the current state of the level. So it's like there's got to be some other way to do it. And in the meantime, so I'd found this other guy who was working on a similar problem, And I emailed him and I was like, hey, this is really interesting. Tell me everything you know. And he said, read these things. So watch old papers. So Lamport 79, that's some important paper that some guy wrote. And a comprehensive study of convergent and commutative data types. That was written in 2011, so that stuff is really new. And this is a really good paper. I recommend everyone to read this. It's actually really clearly written and quite easy to understand. I'm not sure if, I don't think anyone who have recommended this has come back to me and be like, oh, you were totally right, you should have read this. You were right, it was totally the right thing to read. Which I think means nobody is taking my advice yet. But hopefully one or two of you will. Oh, Paulo's read it. Okay, good one. Yeah, it's important to find, there's Twitter and all that aggregation crap, but it doesn't matter. The single best way to find really good content is to ask smart people to recommend it to you directly, and then read it. Okay, so this is basically from the Lamport paper. So this is the meaning of concurrent. So these arrows are messages, and the letters are states, and each section is a different machine. So there's this machine, and it has state A, and then it sends a message to the second machine, and so there's no way for the machines to communicate apart from sending messages, to affect each other without sending messages. So C and D are physically impossible for them to have caused each other. They're totally independent. So you get this kind of, so you can't really say whether or not they are before. Like, they could literally have happened at different times, so they could be before and after each other, but they couldn't have influenced each other's thingness. So you can say these things, like, so A is before B and before C and before D, but you can't say that C is before D, or vice versa. So that's what we mean by concurrent. Now, right, so given that idea, so we get these concurrent things, we need to somehow join them back up again, like this. We need to create the G. But what's a simpler way than doing it than having a three-way merge? So that's where the comprehensive study of convergent and commutative replicated data types, or CRDT, comes in. So what you're doing is you're designing data structures that are trivial to merge. So you don't need to do anything clever just to be like, okay, we've got these two things happen differently, let's just mash them together and now we have a new thing. So let's just design things that work like this. Then we'll have eventually consistent, everything will be eventually consistent, it will just be easy. So this is the simplest, this is the canonical example I like to use. So grow only sets. Sets that can only get larger, say like the set of non-virgins. Once you've become a non-virgin, no other event can change that. So if you are replicating data like this in multiple distributed servers, as soon as you find out about an event that affects non-virginity, then you know that the state has changed, and that state's never going to go back. So you don't need to coordinate. Like, this sort of stuff is just by like you expect, and we can move things in the list, and then here we're pushing meet onto done, which now this is the key thing. This is more like this isn't like a standard array, because arrays don't really work for this situation, but linked lists do. And arrays don't work because when you insert something at the start, it changes the index for everything in the rest of the list. So that doesn't commute well. You need to keep track of the history like Git does, and that's too complicated. So instead, you have a list which each item can appear once, and if you push something with the same ID as another thing, then that is the same thing. And instead of sorting it by just its position in the list, you have a property, a sort property, which you run sort on, and it puts things in the right place. And if you just make this a string, you can always arbitrarily create a string. Well, it's like, there's an infinite number of numbers between 0 and 1, and between any two numbers there's an infinite number of numbers. So if you use this you have to use number of strings so they can be as long as you like, but then you can always insert things between other things. So it's just like a list. Also, it maps really well to UI elements, because UI elements in the DOM are also a linked list. So they have pretty much the same behavior. So that was CRDT. And then I was like, hang on, I need to make this simpler. So I made this thing Scuttlebutt, which sounds like a nonsense word, but it's actually from a paper, also by Amazon. And it's a base class for replicatable data types. So there's two things here. There's I just included these as examples for, like, this is how you would extend this if you wanted to, but then people started using it. So now it's features. But this thing is like a key value store, and this other thing, it's like a reliable event emitter. Like, you can emit an event when there's no network connection, and then when you reconnect, then the other things will receive the event. So everything gets through, and it's great. It's like you could use it to build a peer-to-peer Twitter or something like that. It would be pretty cool. Okay, so this was way simpler. It worked way more closely to the DOM, but I was like, we can make this even most recently received heartbeat from each node. So it's just the IDs of each node, which is just its host and port, and then the timestamp it's last received, and it just iterates over the beat, the objects in beat, and if the beat is more recent than the current heartbeats, then it updates the heartbeat and returns and adds it to the change if this happened. So that's all. That's pretty simple, right? Yep. Yep. Right. So this is just some stuff to connect together the streams, and that starts the server. Then, so if you've passed an initial port, then it will. If you passed an initial port, it will connect to another server. That's important to get things started. You've got to introduce pairs, and then every 3,000 milliseconds this happens. So it just connects to a pair, just makes a TCP connection to a random to the pair that you've decided to connect to. Then, yes, because it connects to initial immediately, and then every three seconds, it connects to the next port that's called. Oh, I think there's a bug there. Yeah, because. Oh no, it's okay. It's okay because this is initial first time. The thing with the gossip protocols is if one gossip fails, it doesn't matter because the next gossip will probably work. So you can be relaxed about stuff like that. So it's just connects to the port, connects to the host, connects up the stream, and then waits for 3 seconds, and then it kills the old stream and whatever was happening, and then randomly selects so it iterates over the other nodes we know about, checks if any of their time, if it hasn't heard a heartbeat from them in a while, and if it hasn't, then it randomly picks one of the nodes that it has communicated with recently, that it's heard from recently and knows are alive, and then randomly connects to one of those for another 3 seconds, and so on. And that's it. And we've got a thing that's actually peer-to-peer. Now, we need to hang more stuff off this, but at least we know what nodes are alive. And you could run this off a whole bunch of servers or whatever, and it would just be that simple, like 100 lines. And the module that it depends on is only about 100 lines or so, and a few other stuff like that. So, yeah. Right. So distributed systems are easy.
Thanks, awesome talk. You made a brief mention of using simple data structures, I guess, to avoid conflicts during the three-way merge.
Mm-hmm.
Could you elaborate on that a bit?
Oh, well...
What do you do to have automatic conflict resolution?
So if your data structures are commutative, then you can just mash them together and there's no problem with merging them. So say like the set of non-virgins. Every time you add something, you just check, because the set can only get bigger, then you get two things that are slightly different, and you just it's the union of them union is commutative. That's one example, and you can do the same thing by, say, each update has a timestamp, and then you can just be like apply that timestamp, and that's really easy. Yeah, and when you have something like an array that has order, you need to do it like that as well. Like you can't do an insert that will shift the indexes. Instead, you have because then you have to track history. Instead, you just change a sort value, and you'll get a similar effect. But read that paper, and it will explain it in a lot more detail. If you read the a comprehensive study of convergent and commutative replicated data types. You can just really skim it. It's quite long, but you can skim it and you can still get the gist. Yeah.
Super. Thank you, Dominic. Awesome talk.